Thank you, Paul, for this introduction. Before I start with my lecture, my presentation, I first would like to thank the Dean of the Department of CDE, Professor TU Delft. He could not be here, unfortunately, but Professor Sylvia is here to represent him. And of course, as well, I have to thank Seatrium to have appointed me as the visiting professor at NUS. And I'm not going to put all the names there, but still I'm very much honored with the presence of the Excellencies, the ambassadors of Norway and Denmark. And also, of course, I'm honored with the presence of the president, of the vice presidents and of the chairman of the board. And what I learned in the VIP room, that I do have a real expert in the audience. So I have to be very careful on what I'm going to tell, because Mr. Gainsborough knows a lot about offshore wind. Okay, having said that, I think I only need to say that I think I have to excuse Professor Xudong-Jan. He should have been here, but he's not able to attend, unfortunately, this evening. He's one of my direct contact persons in NUS. Okay, then I think we should get started. And what you see is I modified the title of my lecture, although it's in between brackets, because I'd rather like to have the name Floating Offshore Wind, the game changer in our future energy supply. That does not mean that I mean that offshore wind as such is not a game changer, but I think we also have to take a look into the local situation, and there floating offshore wind might be a good way to go. As already said, I'm going to start with the technology developments. And the best thing to do that is by pictures. These are covers of a magazine that dates from 1994, 1995. And this is how wind turbines looked in the Netherlands 30 years ago. You might say, okay, what actually has changed? Because at first glance, they might look pretty much the same. Well, that's only the eye. There are some differences. They are about the size of this indeed old Dutch windmill. So that's about 25, 30 meters diameter. And they are stupid in the sense that they are directly coupled to the grid. So they run with the grid frequency, of course, with a gearbox in between, constant speed, nothing to control. Actually, the grid controls the wind turbine. And the cost is difficult to say, but it was around 50 cents per kilowatt hour, which is something that nobody is willing to pay. Despite that, the development started with these machines, of course, with subsidies and so on. Why? Well, because it is a promising technology, but then you need to do it in order to get the cost down, of course. Where we started, it was classical. Classical meteorology, long-term data. Usually, meteor institutes can provide you with good information in the first, let's say, 50, 60 meters of the atmospheric boundary layers. But as soon as you go higher, you don't know what's going on there. Yes, we are very good in aerodynamics, low-speed aerodynamics, but we need different airfoils. Fatigue characteristics, that's what we have, but for conventional material. And we use classical electric designs. After this research over, let's say, 20 years, we got a lot more. We got wind-specific data up to the larger heights in the lower part of the atmospheric boundary layer. We were able to design and test and apply thick airfoils, things you never see in aircraft. We worked on fatigue loads on composite structures, because you can imagine that these composite blades, during their lifetime, they get a large amount of cycles, typically around 10 to the 9 cycles. And it is as if you're sitting in an aircraft and the aircraft flies through turbulence, and you continuously experience that turbulence over a period of 20 years. But you can imagine that this is something that we really did not know how to deal with that and how to design with that 30 years ago. And also the whole electronics came in, so that then we were able to design machines that had also a rotational speed that could keep pace with the wind speed. And that's important for two things: better performance, but also reduction of the loads. Okay, so aerodynamics in Air Force was important. Fatigue, blade fatigue testing, because you can do a lot on a computer, but you need to do the testing as well. And of course, the movement into generators, even to direct drive generators, which are directly driven by the rotor. So skipping, mitigating the gearbox. So there's what we got after 20 years in 2005. Major achievements, dedicated wind turbine designs and tools and research labs. Sufficient size, 1 megawatt plus, which is tiny with today's view, but that was really the step that we need to take in order to learn. Modern technology and performance is becoming better and better and becoming more economic. This is an example I like to show quite often, and I need to draw your attention to this over here. This is where it started, and this is what we got in 2015. So really a big difference, not only in size, but also in terms of the design, because you can see this large nacelles with the direct drive generator in it. So what we got is a factor of 40 in power, a factor of 80 in production, and a factor of 10 in cost reduction in about 30 years of R&D. And I used to work in Delft in the Faculty of Aerospace Engineering, and the next slide was a very nice slide to tease my fellows that work on aircraft. Because what did they do actually after the Second World War? Well, they went from the nice Lockheed Constellation, which was just designed after the Second World War, up to the right one, which is an Airbus A380. That's the largest commercial aircraft that we have. Yes, a factor of 20 in passengers. Yes, a factor of 2 in speed. But they needed 60 years. So really, we did really a good job in wind energy R&D to speed up and come to pace and come to, of course, affordable costs. So what we got is integrated wind turbine design methods, which means that you integrate the aerodynamics with the dynamics, the aeroelastics, with the control. We built the largest rotating machines on Earth. The left picture is an example of that. We made the largest composite structures on Earth as well. I mean, a single blade of a modern 20 megawatt wind turbine is longer than 120, 130 meters. One single blade, where the complete span of the largest commercial aircraft is only 80 meters. Well, we're now about to produce 50 megawatt plus commercial machines, series produced. And when you put them offshore, you need these, and you can see that on the bottom, huge offshore monopile structures. They have a length of more than 100 meters now, and diameters up to 10 meters diameter. Okay, this is just for the general audience to show what would happen if you would put one single 15 megawatt wind turbine on the skyline of Singapore. This is how it looks. I mean, this is not something I propose, but just to give you an idea about what kind of things we're nowadays putting on a weekly basis offshore in Europe. Yeah, where are we now? Oh, this is also something I could say. One of these wind turbines now let me say it the other way, 10 of these 15 megawatts wind turbines per year can completely compensate for the growth of the energy demand of Singapore. That's another way of looking to the skyline. This is what we can do nowadays. Okay, then where are we now? Well, worldwide, wind and solar in terms of their production, are about equal. They both are nowadays producing about 10% of the energy demand. At a cost which is around 4, 5, 6 cents, depends a little bit. Offshore is still a little bit more expensive than onshore, and solar, that strongly depends, of course, on the influx, on the solar influx that you have. But here in the Asian region, the dotted line is 2025. You still that there's still a lot of coal and gas. Unabated coal means that you don't have carbon sequestration and storage. So yes, there's something to do. And the International Energy Agency, they pledge for a scenario to pick up speed from now up to 2040, 2050, 2060. What always also surprises me when you go into, for example, governmental papers or other papers here in Singapore, they still talk in Singapore about alternative energy. Wind and solar is alternative energy. That's the wrong way of thinking. I mean, we should go into the direction that we're going to consider fossil fuels as the wrong alternative and the renewables as the right one. And we've seen this turn of thinking already in Northwestern Europe something like 10 years ago. Nobody is talking anymore about alternative energy in Europe. And this is the way to go and also the way to think. Okay, yes, there's a long way to go. This is the Asian electricity generation by source, and wind as solar is still tiny. So everybody in this audience, pick up what you can do and make it better. Make this graph speeding up with much more wind and solar energy in the coming decades. Now I'm not talking about wind in general, I'm talking about offshore wind in general, which is pretty large in Northwestern Europe, but worthwhile is still coming up. It's a fairly new technology. About 60 gigawatts, 60 power stations are now in operation, 55, 60, and a lot of it is happening in China, as already Mr. Gainsborough told. New installations for a large extent are from China, but also, luckily, some other issues with respect to, for example, floating offshore energy in Korea. But then floating offshore is only a small fraction of what's offshore at the moment. So again, in terms of technology matureness, offshore wind is, but floating offshore wind is not yet. And that's yet another area to work on, I would say, from the Asian perspective, and probably also from the Singapore perspective. I'm going to disappoint you, because this is a picture of what we call the wind atlas. So that provides you with the information of the resources, wind energy resources, at already a height of 200 meters. And over here is Singapore. And red is good, and yellow and green and blue is bad. Okay, that's bad luck, isn't it? Why? Why is this? Actually, there's not much that we can do on this. This has to do with what they call, the meteorologists call Hadley cells. It basically means that the major velocity in wind that we have near the equator is vertically upwards. And then, you know, the wind speeds that you find on the surface, in the lowest 500 meters, are not over here, but as you can see on the graph, are more in this area and in this area. So, of course, then the obvious question is, why? Why look into wind from a Singapore perspective? Well, I would say Singapore is doing something already. This is, for example, a kind of, it's not an oil and gas platform. This is what's called an HVDC platform. It's a complicated name for a plug, high voltage direct current, of 2 gigawatts. So this can capture the electricity from 2 power stations. In this case, these are two power stations that are going to be built in the North Sea. The platform is already there. It has been designed over here at Seatrium, shipped to Europe. It's owned by TenneT. They purchased them. They've put them already, and then the offshore wind farms to come are going to be connected with this platform. And this is Singapore industry, isn't it? This is what you can do in Singapore. So yes, there's something to find in Singapore. But then, if we think one step further, look into floating offshore wind energy, that really can become a game changer, also for the Asian area. What's floating offshore wind energy? This is a pretty old graph, because we learned a lot about wind turbines that are fixed to the ground. Actually, now we build them up to 45 meters water depth, and with a slightly different structure up to 60 meters. But as long as you go beyond 60 meters, or if you go farther offshore, you might need to go to floating. So these are actually floating structures, which are, well, moored as it's called, so hanged with anchors or so to keep it a little bit on place. But for the rest are moving with the wind and moving with the waves and the currents. As I said, this is a technology in development. About 250 megawatts currently installed. I give two examples, just to give you an idea about how it looks like. One of them is, yes, Mr. Ambassador from Norway. And unfortunately, I don't have an example of offshore wind in Denmark, but they're for sure building offshore wind, bottom-fixed offshore wind farms to a large extent as well. The other one is from Portugal. Okay, this is how it started in Norway. This is the plan of Norway on the southwest in Karmøy, with what we now call a pretty small machine, only 2.3 megawatts. And this one is about 100 meters tall, but it's also 100 meters deep. And Norway, of course, has its fjords. So that's why they're able to build a floating offshore wind spar-buoy structure, as it is called, in the harbor area. 100 meters, a huge displacement. It was built. It was towed out. This is also something you can do. Simply build it on a location where you can do proper work, and then sail it out, bring it to place, and then get it in operation. This was the first one, the demonstrator. Then, a number of years later, 2017, they started to build the first floating offshore wind farm. So a number of wind turbines together. They were built in Norway as well, sailed over the North Sea, and then they were located over here on the northeast side of England, actually it's Scotland, to operate there in front of Aberdeen. They have been operating there for a number of years. It was not completely without problems, but again, offshore wind, floating offshore wind is a learning process. You learn not only behind your computer, you learn by doing experiments, scaled experiments in wave tanks, in towering tanks, and by doing it in practice, of course. This is the latest phase, this is the third phase. It's 11 wind turbines of 8 megawatts, and here you can see the parts, these are the parts of the tower are brought together. These are the floaters, the spar-buoy floaters, which are also manufactured in the harbor. And then you need a huge, huge crane, of course, because these things are really large, to just assemble them. And the blades, they need to be taken on place as well. And this is only 80 meters. I mean, they're almost twice as large nowadays. And here you can see the building up. And in the end, the location. And I do have a little bit of problems in showing this picture. Why? Because these 11 wind turbines of 8 megawatts are used to power an oil and gas platform. So, does this contribute to renewable energy? Maybe not directly, but indirectly, of course, they do, because we learn. We learn how to build these things, we learn how to install them, we learn to operate that, and that's, I think, why in the end I'm still positive about this project. What is even nicer that there are a number of numbers in this table, but you should look to the last ones. The first one, the demo, was very expensive, 30 euros per megawatt hour. The last one was 1/3 of it. So there's a very steep learning curve by doing this, by making it happen. And this is something to keep in our mind as well. If we really want it, if we start doing it, we will see a very steep learning curve. The other one, this is the Portuguese one, also started with a demonstrator. So this is the second learning thing. You need to build a demonstrator first to learn things and then scale up. You see, it's a different design. It has 3 floaters. And wind turbine, this wind turbine is on one of the floaters. They have their reasons for doing that. And you have, again, this kind of mooring system with anchors. It's only a 2 megawatt machine, again, similar to the Danes, to the Norwegian people. It was constructed in 2012, and again, built in the harbor and then sailed out. Later on, they built a second phase, which is 8 megawatt. That was considered to be very serious in 2019. Now 8 megawatts, okay, you can buy it, but you better buy a larger one. 3 ones in the same way constructed, and here you can see some details to give you an idea about the size of these floaters. Inspection, that's also an advantage. You can do a lot of inspection in the harbor. That's a lot cheaper and easier. And then in the end, of course, you need to do some inspections on site as well, some part of the commissioning. And again, sailing them out and having them in operation. So yes, floating offshore wind exists already. And we're learning a lot. I cannot go into all the details, of course, of the technology. If you really want to do that, come and see me in the end of this year or beginning of next year for my lectures, because then I'm going much more, of course, into the dynamics. But I will just give you some kind of an idea, a grasp of what is going on. And this is, of course, what happens with these type of floaters. They will move with the waves. And then, of course, you can compensate to some extent for that, but you also need to take into account, for example, the dynamics and the control of the wind turbine to be compliant with this. And this is still a learning process. We know a lot, we learn every day, and it's getting better and better. This is another example in which you start using the different control options that you have in a wind turbine to control the movement of the floater. It says on top, as you can read with me, IPC, individual pitch control. Well, that might not ring a bell to everyone, but I'll try to explain what it is. Pitch control, that's something that wind turbines do have nowadays. And it basically works like this. So you're looking inside of the hub, and here you can see that these blades are actually pitching. This is control, and all 3 blades, they pitch at the same angle. That's old-fashioned already, because nowadays we can individually move each blade. This is something, of course, that you need if you realize yourself that the lowest part of the modern wind turbines is at 50 meters height, and the highest is above 300 meters. There will be a big difference between the wind speed, for example, and you can compensate with that by pitching during the revolution. So basically, we are using advanced controls in a similar way than aircraft, because also aircraft compensate for turbulence, but we do it much smarter, because these blades are morphing, and we pitch the complete blade to be able to reduce fatigue loads and still optimize performance. But once you do that, you can also use that to control the movement of the floater. And this is what you will see in a moment in the left graph. On the left-hand side, there's a land-based controller in the machine, and on the right-hand side, there is a controller that makes use of this individual pitch control to control the movement of the floater. So there's a coupling between what you do with the rotor and what you do with the floater. And you will see that the left three pillars of this tri-floater are starting to drift off, while in the right one, they don't do it. This is the action of the wind turbine that keeps actually the floater in place. I'll show you. So now everything looks fine, but you'll gradually see that the three yellow parts over here are starting to rotate, while they don't do it over there. And this is a question of the loads on the floater by the currents and the waves. And if it happens, you don't want this, you can mitigate that by this IPC. So this is actually what's the fun of us as researchers, to try to optimize this combination in such a way that your costs are going down further in the end, because you can design more optimal, not only for the rotor, but also for the floater. Okay, yeah, I already said something about it. Is there something happening already? Yes, there are things happening, also in terms of floating offshore wind in this area. This is an example of a project in Taiwan. It's not yet there, and it's still fairly small. It's only 15 wind turbines or 12 wind turbines of 15 megawatts. But still, and you can see the same concept, the type of tri-floater. And this is a slightly different design because there's a fourth support structure actually for the tower. You have these different design options, then we need to optimize that already. So this is something that is going to be in operation in, let's say, 5 years from now, 4 or 5 years. And there's another one, and this is a more serious one in the sense that we're talking about 1 gigawatts. So yes, the size of a commercial power plant. And you can also see that already from the size of the component. This is, the mold of one blade. That's a person over there. This is the size of the nacelle, where the generator is in. This is a Danish one, Her Excellency. So we also have some Danish content in it. And of course, the Dutch, they do the geosurvey. And these are modern meteor stations. So you put them offshore. This is what we learned. They have a lidar on top, and they measure the vertical boundary layer so that you don't need the classical towers anymore to get the information you need to be able to design them and to be able to predict the production. Okay, so this is happening in, well, maybe the local area, but it's at least happening in Asia. And I think it's a good thing. Where do we going to use this floating offshore wind energy for? In Europe, the ultimate plan, together with the Norwegian people, the Danish people, the UK people, the German people, and everything, is in the end to come to 320 gigawatts. 320 power stations in the North Sea. That's huge. It's probably too much for our electricity demand. So we need to do something, and we also might need to do something in terms of the storage. Okay, this is a cartoon I found a number of years ago. 5 years ago, hydrogen was a hype. So if you can't read it, the teacher says, before I ask the question, can anyone anticipate on the answer? There's a smart student who says, hydrogen. That was typically the situation 5 years ago. And it's still there to some extent. And yes, not yet floating, but offshore platforms are already designed. This is a Belgian one, to be used in conjunction with offshore wind farms to produce hydrogen offshore. It's not yet there, but it's serious. Then hydrogen is fantastic if you would have it in abundance. But, I mean, apart from electricity, we also want to decarbonize, for example, the steel industry. We want to decarbonize flying, because we all still feel a little bit or maybe more guilty every time we take a plane. And this is what I also feel to some extent when I come from Holland to Singapore. So we need to do something there as well. And shipping is a key issue as well. You could try to do that with hydrogen. And the red numbers are the numbers that you see that would be needed in proportion of what we nowadays produce in electricity terms in solar and wind together. But then you would need about 5 times the current global production from wind and solar. So once we get the cost right, there's a huge market. But then the question is hydrogen always the issue? Still, the costs are far too high. Electrolyzers are getting larger and larger and larger, but you know, a 1 gigawatt hydrolyzer is not yet there. So you either need to do that onshore or something else. And transport is an issue as well. Yes, if you have a pipeline, fine. But if you don't have it, you need to build hydrogen carriers to bring it from the location where you produce it to the location where you need it. And these things can be made, but they are complicated, mainly because of the fact that you need to cool hydrogen down up to almost the 0 point, by minus 273 degrees, to make it fluid. And transporting it in a gaseous way doesn't really pay off in terms of the energy content that you have. And basically, this whole hydrogen is a chicken and egg issue. If we really want to go forward with that, and I hope it's going to happen, at least in Northwest Europe, then you will see the costs going down as well. It's still a kind of an issue. And due to geopolitical reasons, we now see some slack, so to say, in the whole development, which I think is a pity, because to me, going not only into electricity, but also going into molecules, renewable molecules, is something we will need in the future. Typically for the spots where we cannot use electricity, for it's too complicated. But then there's another thing, that's ammonia. Ammonia has some advantages. It's easier to transport because on minus 30 degrees it's liquid, and minus 30 degrees is not really difficult. It has a higher energy density when liquid than hydrogen. There are many applications already, mainly fertilizer, but it's also already used for engines, fuel cells. And the good thing is there's an existing infrastructure. We already use ammonia to some extent. And yes, you can make it with H2 as well. Yeah, some issues. It's toxic, it's flammable. So there are all kinds of safety issues, corrosive, and integration with the other infrastructure is maybe more challenging. So, but this is really something to discover as well. So do not only think, as the students in the teachers' hall, to hydrogen alone, also look to ammonia. We have had, of course, a student that did some studies on effective application of ammonia as a marine fuel. And then you might say, is this guy nuts? Are we ever going to use ammonia as a propulsion fuel for ships? And then I have to refer you to last year's public lecture, which was given by the head of DNV Energy Transition, by Remy Eriksen. And he showed this graph. At the moment, yes, ammonia and hydrogen is negligible. It's basically not happening a lot. This is for the ships in operation. But then, and these are his graphs, for ships on order, half of them is looking away from the conventional fuels. And there you see a huge increase of what they expect or what they see in terms of ammonia. So ammonia might become important for ship propulsion. And yes, of course, Seatrium also works already in the ammonia field. This is a approved design of an ammonia bunker that they're going to be built. I don't know exactly for whom, but Aziz knows probably where it's for. So yes, it's happening. So green ammonia from offshore wind on the long term can also become a serious business case. And then think a little bit out of the box. If you're not longer restricted to electricity cables, you can generate renewable molecules virtually everywhere in the world, sail them to where you need, and use them. So there is a vision, a long-term vision, for using wind power in Singapore as well. generate it where the wind is, transform it to molecules, sail it to Singapore and use it. And this is more or less what I would like to tell you. Some takeaways. This is what I learned. I mean, when you are a teacher in university, they also learn you learning practices and so on, and we always have to conclude with takeaways. So these are the takeaways of this evening, I hope. Offshore wind is a mature industry. It's competitive, but at high wind locations. Floating offshore is coming. It's still in development, but it's coming. Cost reductions of a factor 3 already are there, and it's going to be cheaper and cheaper. Offshore production of molecules, renewable molecules, seems to make sense already, with bottom fixed and in the North Sea. Might come in place as well, may come into the picture as well on the longer term, also in other areas. And you can use them in very, very different ways. Not only renew the electricity supply, but also renew transport, etc., as I showed. And this could also be a way towards a sustainable Singapore. Okay, I hope I'm still in time. I'd like to conclude with this graph. Again, with a cartoon, which is a little bit of a joke. But thank you anyway for your attention.